Conditional, probability, intersection, and independence. Example 1 says a single card is drawn from a standard 52 card deck. Find the conditional probability the card is a spade, giving that it is a 7. Okay, so let's talk about cards, a deck of cards. A deck of cards has two colors. You have a red and you have black. We have 4 suits. The reds are hearts and diamonds. The black is a spade and clubs. They go from ace, king, queen, jack, 10, ... all the way through to 2. So there's a total of 13 cards in each suit. So we're going to start this probability by looking at the probability, and we're going to label these things. So let's just label it first. Let's just go there first. Let's call an element A as 7 and B as the spades. Now I chose B as spades because the spade is talking about the group of cards we're going to be looking at, right? And there's one specific card we want to pull from it, and it's going to be a 7. So A is 7, B is spade. Now we're looking for this probability that we have this group B where A comes from that group, okay? That formula is going to be the, write it down right, the number of elements where A intersects B divided by the number of elements in A. So let's talk about that. What is the number of elements of spade and 7? Well, in a group of spades, I said there was ace through 2, right? Ace, king, queen, jack, 10 through 2. There's only going to be 1 7. That makes sense? There's only going to be 1. But when we talk about the whole deck of cards, and when you know how many 7s are available in the whole deck of cards, well, there's 4 groups. So there's going to be 4 7s because there's only 1 7 per group. So now let's look at that. We have the probability of the spade, the group of spades with the 7 in it, which we called it the probability of BA is going to be 1/4. We just figured it out right here, right? Right. And if you need me to, let me just write that number of spade. And 7 divided by the number of elements of 7s. There we go. And that's how we got the 1/4. So therefore, the probability that card drawn is a spade, giving that it is a 7, my answer is going to be 1/4. Okay, let's do example 2. A single card is drawn from a standard card, 52 card deck. Find the conditional probability that the card is a heart, giving that it is black. All right, so we just talked about a deck of cards, right? And hearts is one of them. I'm going to go ahead and write the formula out, but some of you may already know the answer right off the bat and save a lot of time, but let's just do the math right quick. So whenever we talk about a deck of cards, we said there's 2 colors, red and black, and there's 52 cards in a deck. And if I divide that 52 by 2, I know that 26 cards are red and 26 cards are black. All right, so we know that much. So the number of elements that are black in that deck of cards is going to be 26. All right, so the probability of drawing a black card, we know is going to be a half, right? Because if I was to set this up and divide this out by the number of sample in that, which is 52 cards, if I divide this out, one goes into 26 once, goes into 52 twice, we know we have a half of a chance of drawing a black card when we draw. Now let's talk about the probability that it is a heart. So the probability that a heart and it's black. We're going to take the probability of a heart and black. We're going to divide it by the probability of black. Well, we already know the denominator is a half. We just got through talking about that. But what about the number of hearts that's black? Well, we just talked, if you'll look above here, we just stated what the colors are. The red is hearts and diamonds. There is no black. So it's going to be 0 here. Anytime 0 is in the numerator, my answer is 0. So that is 0. The probability given is 0 here. Let's do example 3. It says compute the probability of D, that we have this group D where C came from it. And we're going to use this formula here. And we are given this table we're going to use as well. So let me write down some formulas. We know that the probability of the event C is equal to the probability of C intersects D plus the probability of C intersects E. And why are we including E? Because we're talking about the probability of C. That means we have to factor in everywhere it is at. And C is in this column right here. So what we're going to have to do is now we notice that we have the probability of C. Well, it gave us a total down here. We didn't have to add it up. It worked out great. Now, if it didn't give us the total column, we would have added up the 0.20 plus the 0.10, which would have given me 0.30. However, they gave us that column. Now let's find the probability of D intersecting C. Well, we got it right here. Here's D, here's C, here's their intersection, 0.20. The probability of E intersects C, well, that is given to us to here, 0.10. Now, we need to figure out what is our answer here. Well, the answer for, I mean, and I just wrote this down. I'm not saying we need this. I just wrote it down, but it's already factored in right here in the total probability. So we don't need it, but I did want you to see it. Okay. Now, let's finish this up. We have the probability that we have this event going on where C came from it. We're going to have the probability of D intersects C divided by the probability of C. So I have 0.20 divided by 0.30. Round to the nearest hundreds, we get 0.67, and that is our probability. Okay, let's do example 4. Example 4 says we have a fair coin toss 13 times. So when we talk about coin, we have two options, right? You have a heads and a tails. It says, what is the probability of tossing a head on the 13th toss, given that the preceding 12 tosses were tails? Okay, so we have this event going on. This formula we're going to use. And remember, probability of B cannot equal 0. If it does, the denominator is 0, then this is undefined and we're unable to solve for it. Okay, so we're going to consider that C and D. So I'm going to change the notation up just a little bit. I'm going to call D. I'm going to put it in the place of A here. So I'm going to do this as we're doing, working on this. And they use A and B on just a notation. And you could change it, just have to be consistent on what you change it to. Okay, so now we're going to let C be preceding the toss. So I'm going to say C. And then we're going to let D be the next coin. The 13th coin. I could have circled it down here. All right. Now that I've decided on what's what, I can turn around and plug in. And now let's find, what is the probability of D? Well, think about it. It said that we're trying to figure out the next toss, the one more toss. So I know, 13 minus 12 is 1, right? Also, I know that a coin has 2 sides, and that's all. So there's only 2 options. So my answer here is probability D is going to be a half. You've got a half chance that the next toss will be a heads versus tails. Okay. Part B here says, what is the probability of getting either 13 heads or 13 tails? Well, we just figured out that either way it goes, we're going to have a half probability of getting heads or tails. We will want to know what's the probability of, if I toss it 13 times, that I'm going to come out with tails. 13 times I'm going to get heads. And remember, the or says that we are going to include them both. So what I'm going to do is take that half, raise it to the 13th power, or you could have said half times half times half. You can go out 13 times. Just this other way is a lot shorter and a lot less work. So it's the same as saying a half times a half. So every time you throw it, you multiply it by that half. So I'm going to go ahead and just make it a little bit easier and raise it to the power of 13. And I get 1 over 8192. Okay. And now we want to know the probability of heads being flipped 13 times plus the probability of tails being flipped 13 times. So I'm going to add these two together. And I get 1 per 4,096. That's that probability. Okay, let's do example 5. 2 cards are drawn in succession from a standard 52 card deck. What is the probability that the first card is a club and the second card is a spade? So first card is a club. Let me just highlight it. I think that would be easier. And the second card is a spade. So whenever we talk about a deck of cards, we know there's 4 suits, hearts, diamonds, clubs, and spades. And in each suit, there's 13 cards. We know that. And we know there's 2 reds, they're hearts and diamonds, 2 blacks are spades and clubs. We will need to perform the conditional probability here, a calculation to find the probability of the intersection of the 2 events, because we do have 2 events going on. The first card drawn as a club, the second one drawn as a spade. And that is, we are looking for the first event and the second event. Also, since the probability of each event is non-zero, we can use the product rule and the events A and B non-zero probabilities. So here we go. This solve for it. We have the probability, and we need to label, right? Let's label it right quick. Let's call C my first card to be drawn as a club. And let's call D my second card drawn as a spade. So we're going to look for the probability of our cards being drawn as a club. Well, there's 13 clubs and there's a total of 52 cards. So 13 goes in itself once, goes in 52 4 times. So the probability of it being C is 1/4, right? So part A here says if the cards are drawn without replacement, right? Without replacement, let's solve it. So if I do it without placement, I know that there's 13 in the group, right? And I know that there's without replacement, that means when I pulled that card out, I didn't put it back in. So now I'm down to 51 cards. So I have this fraction. So now we can solve the final question here for this one. It says we're going to take the intersection of the clubs versus the spades, and we are going to take the probability of the clubs times the probability of that these cards come from the spades and the clubs come. And that's what I get from that deck, that group. And let's round to 4 decimal place, 10,000s. All right, so that answers that one. That's without replacement. Let's do the next one though. The next one says with replacement. That means we put the card back. So we still got the probability because we're still working on the same assumption, the same application problem here. So we got 1/4, and we know that this here is also 1/4. We've already solved it up above. But it changed a little bit, right? Because it was without replacement. Then, let me, I skipped a step. I really need to show this part. We solved C already, but this one here that from above was without replacement. This one is with replacement. So it actually 13 cards in a suit divided by that 52. This is how we get the 1/4 here. All right, moving on. Now let's finish this up. We're going to take this formula. And multiply 1/4 times 1/4. Let's get to the nearest 10,000ths. And that is the probability with replacement. Okay, example 6. In a study to determine the frequency and the dependency of color blindness relative to females and males, 1,000 people were chosen at random. The following results are recorded. So we're given this chart here, and we're going to convert the table of probability by dividing each one of them by 1,000, because we're going to put it in probability form. So what this tells me is that every one of these numbers, we're going to divide it by 1,000 because it said that 1,000 people participated or was chosen at random. So that means I'm going to take that 6 and divide it by 1,000. And whenever you're dividing by ones and zeros, you count the zeros and you notice that you're going to move the decimal in this direction that many places. So this gives me this. So that's a little bit quicker because you can go 1, 2, 3, and just keep going. And that would make it easier for you. Or you can just divide it by 1,000. Oops. All right, so now that we're getting this in probability format, we can move on to the next part. All right. B says, what is the probability that a person is a woman, given that the person is colorblind? Are the events colorblindness and females independent? All right. So you're given a formula there. So let's solve for it. What we need to do is label right quick. We're going to let F equal the event that the person chosen is a woman. Let's let C be the event that the person is chosen is colorblind. All right, so now let's solve. So I have this probability formula. So when we go look at it up here, it says the probability that the female and colorblind intersects, right? That's what we're looking at. Now, if you look up here and see females here and where the colorblind, they intersect right here. So I got 0.006 divided by, and then the probability they're all colorblind, or, you know, the total colorblind, we got it right here in the totals columns. Okay, so now we're going to divide that. Let's go out to the nearest thousandths. All right, so now we determined, so now we can determine if it's independent or not by comparing. Let me make a note right here right quick. So that was our probability, okay? So now let's determine if it's independent. If this is independent, it's if and only if the intersection of my F and C is equal to the probability of the females times the color blindness. So I have the probability of the females versus the color blindness, right? So we need to determine what is the probability of the females times the probability of color blindness. Well, if you go up here to our table and look at our totals for the females right here, we get 0.656, and we're going to multiply it by the total number of blindness here, colorblind. And when we multiply those two together, I get 0.027. Well, we want to know, is it independent? Well, the only way it's independent is if these two numbers are equal. And if you notice, they are not. So this is a dependent case. So let's solve C. It says, what is the probability that a person is colorblind given the person is a male? And on this table here, if you'll notice, the male is the F complement. So the event that the person chosen is male, or is a male, or man, is a man, I believe is what it said. All right, are the events colorblind and male independent? So we want to know if they're independent. So now that we know that the F complement is the man chosen for it, we're still going to let C equal the event that the person chosen is colorblind. Okay, so now let's use this formula. We have our probability that we have males that come from in the group of colorblind. So we want to see if they intersect. And if so, what is that number? And then we want the total on the males. Well, let's look. The colorblind and males, yeah, they intersect at 0.035. So, and then we want the total number of men. If you'll look here, it's 0.344. And let's type that in our calculator, or you could do it by hand on paper. So we get this probability. Now we want to know if it's independent. Well, let's find out. So if I take the number of, the probability of the colorblind times the probability of males, right? Let's go back up there. The probability of colorblind is 0.04. And then the number of males is 0.34. So let's multiply those two. 0.041 times 0.344. We get 0.014. So approximately. And this is dependent because these two are not equal. So it's not an independent case, it's dependent.